Okay, this is attempt number 2 to record a video about least squares regression. So the idea is that when we measure some variables, let's call these variables x and y, we may see that there is some relationship, some correlation between these variables. And when we see something like that, we may see a scatter plot that looks something like the following, in which higher values of y are typically associated with higher values of x. Not deterministically so, but as a general rule. And lower values of x are associated with lower values of y. Now, this isn't the only relationship that would indicate a correlation. Of course, you could have the entire reverse of this, in which things would still be strongly correlated, right? Something like this, in which high values on y are associated with low values on x, and high values on x are associated with low values on y. In either of these cases, there's a strong correlation, and when there's a strong correlation, it means that if you know something about x, in this situation, for instance, if you know something about x, you can make a pretty good guess about y. So if you know that x is going to be high at the same time y is likely to be high, then if you observe a high x value, you can make a decent prediction that the y value is going to be high. So these sorts of relationships exist all over. And when you have this kind of relationship, we can use a really powerful statistical model called linear regression. The job of linear regression is to try to fit a line through the scatter of data to do a good job at making predictions. Now, when I say a good job, what do I mean? Well, there's a couple of different ways you could think about that. And the way that we're going to talk about in this particular video is the classic way. So what I mean is that if we have a scatter of data of x and y, we have many, many possible lines that we could draw, right? We could draw a line here, we could draw a line here, we could draw a line here. Those are all lines that go through or around our data, but they're not very useful. At least they're not as useful as they could be, because what we want is a line that's going to take as good of information as it can from x to make a guess about y. And so the way that we're going to approach that today is we're going to look for a line that predicts y in a way that makes the least amount of mistakes. And what do I mean by mistakes? Well, we can think about it like this. Let me clean up my drawing just a little bit here. So if we have all of this scatter and we draw some line through it, as I've done here, if this line is our guess about y using information about x, we can see that it's rarely perfect, right? Only maybe one of these points does it actually go through an actual y value, or an xy value. So the rest of the time, it's making some amount of error, right? There's some non-zero error between our guess, where the line is, and where the actual point was here. Same thing here, right? Same thing here. All of these little lines are errors. They're errors that are being made because our line through the data isn't perfectly capturing those values. Now, if we drew some other line like I was talking about earlier, if we drew some line like this, well, this line is also going to have error, and it's going to have a lot more of it because it's going to be, in total, much further away from all of these values than the other line that I drew. So what we're looking for is a line that's going to minimize the errors. So it's going to minimize what we would call residual values, the distances, the sum of the distances, if I can say that, from our line to our points. So how do we do that? I'm going to clean this up so I can redraw it. So how do we do that? Well, we use calculus. So if we define our equations, let's actually start writing things down now. So let's say that we have some yi, right? I indicating that there's an ith value for each observation point, and we have some n of them. So, if we have 10 people, I would go from 1, 2, 3, all the way to 10. So if we have some ith y value, we're going to say that this point, whatever it is, if this is the first point, this is the y1th value, we're going to say that y1 is equal to some intercept value, which we'll call b naught or beta naught, and then there's going to be some slope, beta 1, and that's where we're going to take our x value, because it's going to use information about x to determine the y, and those x values are going to be similarly indexed using I. And there's going to be some error term, and that's because, well, I shouldn't say that's because, but we'll define this error to have an expected value of 0. And the reason that we do that is when you see that, then you know that the expected value of yi is equal to, if we treat all of these components as constant, then the expected value can be nothing else but b naught plus b1 xi, right? Because that expected value of those error terms are just going to be 0. So what this really is a model. This is really our model, and this is the model for the expected y ith value. So when we create this model and we get estimators for our beta naughts and our beta 1s, we usually denote things thus. We usually call it y hat or yi hat, and yi hat is usually defined to be beta naught hat plus beta 1 hat xi. Okay, so when we left off, we had just defined this equation here. And this equation here. And where do we want to go from this? So again, earlier I said that what we're looking for is a line that minimizes the errors, that minimizes the total sum of errors. And now we're gonna define mathematically what we mean when we say an error. So as I've just said, this right here, this is our model. This is the model, the equation for the line that we can see drawn up there. Or rather, we're gonna find the parameters that do that for us. And when we do that, we're gonna have that there's some true y-ith value that I might as well just draw it. So again, if we have some scatter, if we have some line that I'm going to call y hat, then if this is some y5 value, then the distance between the line defined by my my line for an associated x5, the distance between that line and the y5 is the fifth error, which we'll denote as e. So for any ith y value, the difference from that y ith value and the associated y hat value is equal to the ith e value. And this is how we're going to formally define our errors. And what we're going to do is, as I said, we want to find the line that minimizes the sum of all of those errors. But it's not enough just to minimize the sum of them, because we want to make sure that we're not canceling things out by accident, right? Because this error would technically, this error that I've written here for E5, that would technically be negative, right? And this error over here would technically be positive, right? They might cancel each other out in the sum, and that's not what we're trying to do. So when I say that we were going to find the equation that minimizes the sum of errors, what I actually mean is we're going to find the equation that minimizes the absolute value of those errors. And for mathematical simplicity, when you're looking for the minimum of the absolute value, it suffices to find the minimum of the square. So what we're going to do is find an equation that minimizes, find parameters for beta naught and beta 1, that minimize this equation here, this sum of the squared error terms. And sometimes people will call this SSE for sum of squared error, or sometimes you'll hear it called RSS for residual sum of squares. It goes by many names, and it's a fundamental concept in linear regression, as we're going to see. So as I've already written out, this equation here can also be written as, and I might as well write the I is equal to 1 to n here. I is equal to 1 to n. This is the same thing as yi minus, right, beta naught plus beta 1 x1, right? I haven't changed anything here. Let's make that a curly bracket. Right, and this is all the same thing. So this is our goal. I'm going to capture this just so we keep it in mind. Copy that and go to the next page. Paste that. Because we want to have that in mind as we go forward. So, how do we do this? Well, like any good minimization problem, again, we're trying to minimize that sum of squared error. We're going to need some calculus. So it can be shown this is a convex function. So it has a global minima, and we're going to find that minima by finding the partial derivatives of our two parameters, beta naught and beta 1, and then solving for them simultaneously. So if we take partial derivative of SSE with respect to beta naught, we're going to get, to start with, we're going to get, using chain rule, we're going to get 2 times yi minus beta naught minus beta 1. Forgive me if I leave out the hat marker. I've distributed the negative here as well. Xi times, and then again chain rule. So once you're inside of this, all that's going to be left is this term's. So the initial chain rule is going to bring down that 2. That's going to give you 2 times all this stuff here, and then for what happens inside, once you're on the inside part of the chain rule, the y ith term is going to go to 0 minus beta naught. So if we're doing the partial derivative with respect to beta naught, which we are, then that's going to go to 1, right? And then plus beta 1 x1, that's all going to go to 0. So all that's going to be left here is a negative 1 where that beta naught used to be. So you can see that this whole thing is the resulting first partial derivative with respect to beta naught. And we're just gonna clean this up a little bit. So you can see that this could be rewritten if we pull that 2 out of there. This could be rewritten this way. So, well, actually, let's distribute that. Let's distribute that sum while I'm at it. So let's rearrange a little bit. So the sum of beta naught plus the sum of beta 1 xi minus the sum of yi. And we can do just a little more to clean this up. So we can use the sum on the beta naughts. Beta naughts are constant, so that's just going to be n times beta naught. Plus we can pull the beta 1 to the front of this, sum of xi minus the sum of yi. Yeah, that's as far as we're going to go with beta 1, or sorry, beta naught. And then, why don't I do a new page? Well, maybe what I'll do, got all this fancy technology. Maybe what I'll do is I'll take all this and we'll copy it. We'll go to a new page. We'll make it just a little smaller. Should still be able to see it in the video. And now we're going to do the same thing for beta 1. So let's go ahead and draw a line. So if we take the partial derivative of the sum of squared error with respect to beta 1, we're going to get something that looks like this. Now again, right, this was SSE up here. Don't forget that that's what we're working from. We're going to get something that looks like this. We're going to do chain rule again. Obviously, the very first part of the chain rule is going to be identical. And then the next part's what's going to be different, right? So inside of this here, this is still going to go to 0. Now this term is going to go to 0. And this term, right, we're going to decrease the power on that beta 1, so that's going to go down to 1, the identity, and it's going to be multiplied by xi. You can barely tell that says xi anymore, but it does. So basically what that means is that we've got an extra xi in here, and when you distribute that negative, this negative here, when you distribute that negative, we've got a negative xi hanging out there. So we can clean this up a little bit. You know what? Let's get that 2 out in front again. Do a little bit of parity. So we get that 2. Let's clean things up a little bit more. Distribute that negative, and we'll have something like this. Negative yi xi, positive beta naught xi, positive beta 1 xi squared. There's a little bit of lag there. Hopefully everybody can see that okay. And then let's clean this up a little bit more. So to sum of beta naught xi plus sum of beta 1 xi squared minus, I just like to have the minuses at the end personally, sum of yi xi. Okay, and then finally we'll distribute those sums. So we've still got 2 just hanging out. Everything's multiplied by 2. We're going to pull that beta naught through the sum. Nothing changes inside. We've still got the sum of the sum of xi plus, we'll do the same thing here, beta 1, sum of xi squared, and minus, nothing gets to get pulled through here since these are all bound to that ith sum. So this is what we're going to use for beta 1 and for beta naught to start. So what's our next step? We need to set these both equal to 0 and solve them simultaneously. So I think, we'll do first thing first. We'll grab these and move them to the next page and continue to clean them up. Or we'll set them to 0 and then we'll clean them up a little bit. So, okay, can I get these side by side nice and pretty? Looks like I can. Hopefully neither of those are too tiny to see. So we've got our derivative with respect to beta naught and our derivative with respect to beta 1 hanging out up there. And I'll draw a line in between them just to make sure that nobody thinks that they're supposed to be related somehow. So again, we're going to set these to 0, set to 0, and organize. So just keep things on the left that belong to beta naught and keep things on the right that belong to beta 1. So we've got 0 is equal to 2 n beta naught plus b1 sum of xi minus sum of yi. We can finally distribute that too. And we'll have 0 is equal to 2 n beta naught plus 2 beta 1 sum of xi minus 2 sum of yi. All right, and now what we need to do, remember what we're trying to do here is to get the beta naught terms on one side of the equation so that we can solve for it. And so let's take the 2n beta naught and put that on one side of the equation. And 2n beta naught. And the way that we get that is we have to move the other terms to the other side of the equation, right? Subtracting from the equation. So everything's going to flip signs. So now we're going to have a positive 2 sum of yi. And that is going to be subtracted by 2 beta 1 sum of xi, right? And now all we need to do is just take these coefficients away from the beta naught by dividing them. So we're going to have 2 sum of yi minus 2 beta 1 sum of xi, and that's going to be all over 2n. And now we can finally get rid of that 2 that's just been bothering us forever, so we can go ahead and cancel that. So we can see that now we've got that beta naught is equal to sum of yi minus beta 1 sum of xi all over n. I'm just going to do one final step of cleanup here because it'll be useful to have those n's in the numerator later. So this doesn't change anything. I'm just going to write that denominator into the numerator by distributing it as a 1 over n. So over here we've got beta 1 over n sum of xi. And now that we've got beta naught done, we still need to work on beta 1. So starting from where we left off, we need to set this equal to 0 and solve. So we'll go ahead and start by distributing that 2 out. So we have 2 beta 0, or beta naught, sum of xi, plus 2 beta 1, sum of xi squared. And now I'm running out of room, but we'll make this fit. Minus 2 sum of yi xi. All right, and now we're going to do the same thing we did with beta naught. We're going to move anything that has a beta 1 over to the left side of the equation, and anything from the other side to the other side. So basically what I'm going to do is I'm going to move this term and this term over to the left-hand side of the equation, but I'm going to write the beta 1 on the left. Hopefully that's not confusing, but ultimately I want that beta 1 to have a positive sign, so I'm not going to subtract by it. So we've got 2 beta 1 sum of xi squared is equal to, and again, the signs that I had before are going to be reversed now, right? So I like to write my positives first. So this is 2 sum of yi xi, and that's going to be subtracted by 2 beta naught sum of xi. I'm going to take the coefficients related to that beta 1, and I'm going to move them, divide them. So I have beta 1 is equal to 2 sum of yi xi minus 2 beta naught sum of xi, and that's going to be all over 2 sum of xi squared. And again, I get to cancel those 2's. So I'm left with beta 1 is equal to sum of yi xi minus beta naught sum of xi all over sum of xi squared. So that is my partial derivatives for beta naught and beta 1 after setting them equal to 0 and organizing. And of course we set them equal to 0 because what we're looking for is that minimum point. And again, we've talked about how it can be shown that this equation has some minimum, and we're trying to solve for that. So by setting equal to 0, we're finding that change, that point where the sign of the change is 0, right, where the change it hits 0, and that'll be that minimum point for this function. So we found the 2 partial derivatives, one for beta naught, one for beta 1 for that point where it's equal to 0. And now what we're going to do is we're going to take these solutions for beta naught and for beta 1, and we're going to substitute one into the other to try and get a cleaner solution. The reason for this is that right now this is kind of tricky since we have beta naught in the first equation and beta 1 in the first equation, and beta 1 and beta naught in the second equation. So if we do some substitution, we can get this cleaned up such that we can solve for beta 1 using just stuff that we can solve for, that we know how to solve for, and we'll see what that looks like. So I'm going to go to the next page where I've already moved this stuff over, so we can see that we've got our beta naught is equal to 1 over n sum of yi minus beta 1 over n sum of xi, and we've got our beta 1's just as we derived them on the previous side. Right, everything looks good there. So what we're going to do, as I just said, is we're going to take beta naught and we're going to sub it into beta 1, the equation for beta 1. And so let's go ahead and get started. So if we have beta 1 is equal to the sum of yi xi minus, and this is where the beta naught comes into the equation, so I'm going to make a bracket here, and we're just going to put everything that was in beta naught into this part. So that's 1 over n sum of yi minus beta 1 over n sum of xi. And can't forget that we've got this sum of xi that was originally multiplied by beta naught. Don't want to forget that. This whole thing is over xi squared. So now we're going to go ahead and distribute some terms. So we've got to distribute this sum of xi to the two places that it can go. I'm going to leave off dealing with the distribution of the negative sign in front of that bracket for now. We'll do one thing at a time. So sum of yi xi minus, and we're going to do 1 over n sum of yi, and now we've got a sum of xi, and that's going to be subtracted by beta 1 over n sum of xi, and we're going to have another sum of xi. And this whole thing is still over, nothing's changed down here, the sum of xi squared. We can see that something, as we start to organize our terms here, we can see that this term here, that's the sum of xi multiplied by the sum of xi, which of course is the sum of xi squared. And just to be clear, the sum of xi squared, that whole thing squared, is not the same thing as the sum of xi squared, the sum of the squared xi's. So just want to make sure that, and I'll go ahead and write this out. So beta 1 is equal to sum of yi, sum of yi xi minus, let's go ahead and distribute this negative over here, sum of 1 over n, sum of yi, sum of xi. Now this is going to be plus beta 1n, and so this whole thing, sum of xi, is squared, right? So there's no ambiguity about it. And that whole thing, oops, let's not make a mistake there. This whole thing is over the sum of xi squared, right? And earlier I was just clarifying that this and this are not equal. The one in the numerator is the squared sum of xi's. So you sum up all the xi's and you take their square. And the one in the numerator is, of course, the sum of the squared values of the xi's. So you square all the xi's and then add them together. All right. So now we can continue plugging away here. And what we're going to do is try and get the beta 1s all on one side of the equation, as we always do, right? So we've got this beta 1 that was always there. We've got this new beta 1 term over here that we're going to subtract by. So minus beta 1n sum of xi, that whole thing squared, right? And it's going to bring with it, well, what might be easier instead of trying to do this whole thing all at once. Maybe I'll break down the steps so that I don't lose anybody. So we've got this this thing in the denominator that we've got to deal with, right? So maybe the first thing we'll do is we'll multiply beta 1 by xi squared. That way we can get out of the denominator. Okay. Sum of yi, sum of xi we're going to still have this term here since we haven't gotten rid of it yet, plus beta 1 n sum of xi whole thing squared, right? So now we have no denominator to worry about, so now we can move over those beta 1 terms, or that beta 1 term that I talked about. It's going to be subtracted on this left-hand side. Right, and we haven't made any changes to these terms on the right-hand side, so we can just go ahead and rewrite them here. All right, and now we can go ahead and solve. So we can see that every term in this left-hand side is multiplied by a beta 1, so we can pull that out, right? Distribution would get us back. Oops. So this is just 1 over n now. Right, if I distribute that beta 1, I'm going to get back exactly what I just had, so we haven't changed anything, which is what we're going for. Never want to lose a term by accident. Right. Okay, now I'm just going to grab this whole thing so that we can go to a new page. If it would work with me here. Copy. Apparently wants to bring both these equations, but that's fine. That won't hurt anybody. Oh, that did better than I thought it was going to do. And we'll erase that extraneous bit up there. Okay, so that's what we wanted, which is excellent. So now we can continue. So what we're going to do now is, this whole thing, this whole giant thing in brackets is now just a term that's being multiplied by beta 1. So we're just going to divide by that. And beta 1 is equal to sum of yi xi minus 1 over n sum of yi sum of xi. This whole thing, this whole right-hand side of the equation. It's doing that thing again where it's not writing what I told it to write. Is divided by the sum of xi squared minus 1 over n sum of xi squared. So this form of the equation is fine. There's nothing wrong with it. We could stop here. This gives us a solvable form of beta 1, and then we could plug it into the equation for beta naught, and we'd be good. However, we're going to go one step further, and the reason that we're going to do that is that anybody familiar with these equations is probably used to seeing a form of beta 1 that looks like this. They probably see a form of beta 1 that looks like beta 1 is equal to the sum of xi minus x bar, which is usually meant to mean the sample mean of xi, multiplied by yi minus y bar. And that whole thing is over the sum of xi minus x bar quantity squared. And sometimes this is written as s xy over s xx, which is the sample variance of xy over the sample variance of x. This is, you know, just to be clear, the sample variance of xy is the estimator for the variance of x and y, the sample estimator, over the estimator for the variance of x, just to make that perfectly clear. And so this is a useful form of beta 1 because these are units, these are equations that we're often working with anyway. So it's kind of handy to be able to just plug them in and run rather than have to calculate this new stuff to get to the beta 1. And it's really not that much more work to get to that form of beta 1, and I'll show you how to get there. So maybe what I'll do is there's really just two things that we need. We just need some identities to make this work. And so I think what I'll do is I'll just prove those identities. I'll just derive those two identities, and then we'll plug them in, and that'll be pretty much all the work that we have to do here. So I think I'll start with the numerator, right? That probably makes the most sense. So the numerator is this stuff. So what I really need to do, maybe I'll select this and bring it to the next page so that we can see. I'm going to run out of room if I don't bring things over. So let's copy that. Let's paste that. We'll make this a little smaller, save us some space. Oops. So what we really need in order for this to happen, should be no surprise, is we need to prove that the numerator of this previous form of the equation is equal to the numerator of this new form, and that the denominator is equal to the new form. So let me set this up so that it's plain in black and white. So what we want to do is prove that the equation on the left is the same thing as the equation on the right. And that amounts to proving that the numerator is equal and the denominator is equal. And we can do that in this case. So what I really want to start with is proving two things, I guess. I want to prove that sum of xi minus x bar multiplied by yi minus y bar is equal to this junk that we have over here, right? The sum of yi xi minus 1 over n sum of yi sum of xi, right? If I can show that, and I can show that the numerators are equal, sorry, that the denominators are equal, then I can say that these equations are equal. Okay, so I'm going to go ahead and do this. So if I start with the left-hand side of this and I expand everything out, then I get that the sum of, and we'll do a big bracket, we've got everything going on here, right? I'm going to distribute this yi, right? This is just FOIL. So I get xi multiplied by yi minus x bar yi minus y bar xi plus x bar y bar, right? all I've done to get that is just, do the FOIL, distribute from these terms. And we still got the sum to worry about, so I'm going to go ahead and include the sum there. And I mean, maybe this was clear to everybody, but I'll write down a really important identity that that I've just been sort of throwing out. So x bar is equal to this quantity here. It's x bar is equal to 1 over n sum of xi. That's what we mean when we say x bar. And similarly, y bar is equal to 1 over n sum of yi. And I'm going to use these as we continue to make this proof. So let's go ahead and distribute the sum before I start to do any substitutions here. So this is just me distributing that sum that was living on the left side of this equation. And over here, right, x bar x bar times y bar, those are both constants. So, if we try and take the sum of those from 1 to n, we just end up with them multiplied by n, right? So that's how that works. So now I'm gonna do that substitution I talked about. So rewrite this first term, no change there. So now I've got this minus x bar, and I'm going to sub that x bar for what we know x bar to be equal to, which is 1 over n sum of xi. And that's going to still be multiplied by that sum of yi. And I'm going to do something similar here. I'm going to substitute that y bar for the sum, or for 1 over the sum of yi. And that's still going to be multiplied by the sum of xi. And I'm going to add to that this I'm going to do double substitution here. So I'm going to have n, and I'm going to have that multiplied by 1 over n sum of xi, and I'm running out of room pretty badly here. Let me erase some stuff and rewrite it tinier so that I can fit this in. So this was, I haven't changed anything, but I need to make this fit. So I'm subbing this all in. So I've got this n here. That's going to be multiplied by 1 over n sum of xi. And I've got a 1 over n sum of yi, right? So, what's going on inside of here is I've got 1 over n twice, sum of xi, sum of yi. So we can see that the n on the left is going to cancel one of these 1 over n's, but it can't cancel them both, right? So I'm just going to go ahead and write this. So that is going to leave us with a 1 over n sum of xi and sum of yi, right? So now I'm going to rewrite this whole thing. Xi, yi minus 1 over n sum of xi, sum of yi, minus another 1 over n sum of yi, sum of xi, right, plus 1 over n sum of xi, sum of yi, right? So we can see that this term, and this term are all the same quantity. 2 of them are negative, 1 of them is positive. So, once we take them and add them together, we're just left with 1 negative of that. So we end up with the sum of xi, sum of xi yi minus 1 over n sum of xi, sum of yi, which of course is what we set out to prove, right? So we're done. We know that what we started with, this right here, this numerator right here, is equal to this numerator right here. They're identical. So that's it for the numerator. So what remains is to prove that the denominators are equal. So let's grab those things again and set out to prove that the denominators are the same. Copy, new page, paste. All right, so now we are setting out to prove that, prove that this sum of xi minus x bar squared is equal to sum of xi squared minus 1 over n and sum of xi quantity squared. So again, we're going to take the approach of starting with the left. So we're going to have a sum of, and this is again just FOIL, this is just taking the square of xi time, or minus x bar, which is just xi minus x bar multiplied by xi minus x bar. So when you do that, you end up with xi squared minus x bar xi minus x bar xi plus x bar squared. And we're going to go ahead and distribute that summed. So we get the sum of xi squared minus x bar sum of xi minus x bar sum of xi plus, and this is a constant, so n times x bar squared. And we'll just combine some terms here. So sum of xi squared minus 2 x bar sum of xi plus n times x bar squared. And we can see that this wait, what did I do there? Right, okay, so what we need to do now is we need to make a substitution. So, I mean, I want to find a way to combine these two terms. And it should be unsurprising that to do that, we're going to once again rely on the definition of x bar. So x bar is equal to 1 over n sum of xi, right? Which must mean that x bar times n is equal to the sum of xi. So I'm just going to sub in that sum of xi is equal to x bar times n into the middle equation here. So we can rewrite this whole thing as xi squared minus 2x bar times n x bar times n plus n times x bar squared. And now we can see that that middle term is very similar to that last term, sum of xi squared minus 2x bar. Well, let's write it in the same form as the other one, right? Make it as apparent as possible. So 2n x bar plus 2n x bar squared minus 2n x bar squared. So we can just cancel one of those positive terms, and we end up with sum of xi squared minus n x bar squared. Now we're going to do one other substitution here. So if I take, we'll just leave the first term alone, and we're going to sub that sum of x bar, sorry, we're going to sub that x bar for what x bar is, which we know to be 1 over n sum of xi, right? I haven't changed anything here. And I'm just going to distribute the square so that I have xi squared minus n times 1 over n squared multiplied by sum of xi squared, right? We can see that that square is just going to cancel with that n over there, and this is going to give us what we sought out to get. So this is going to be minus 1 over n sum of xi quantity squared, which of course is what we were trying to get, right? So now we've proved that the denominators are equal. And if the numerator is equal and the denominator is equal, then these two equations must be equal. So that's it. We're done. We can accept that this equation here, go ahead and copy that out. We can accept that this equation here is true, which is awesome. And we can go back to the last equation we had for beta naught, which is this one here. So we can take this equation for beta naught and we can see, I mean, we'll clean this up just a little bit more now that we've covered what sum of yi is equal to. So, right, beta naught is simply equal to y bar minus beta 1 times x bar, right? So we can see that once we've solved for beta 1 using the sample variance and sample covariance formulas, we can then plug that into the equation for beta naught and be on our way. So what we've learned is how to derive the least squares estimators for a linear regression problem, which is pretty cool. And in our next video, we're going to go into the matrix form of these equations. And that comes into play when we have more than just one independent variable, more than just one x variable that we need to worry about. Thanks for tuning in.